Ever been in a conversation where people talk about VTAC, turbolag, or limited slip differentials, and you find yourself just nodding along? It can feel like they're speaking another language. Many videos explain the basics, what a steering wheel or a tire does, but they often skip the complex systems that truly define how a modern car performs and feels. This video is different. We're going to bypass the obvious and dive straight into the engineering heart of the automobile. My promise to you is that by the end of our 10 minutes together, you'll not only understand these terms, but also grasp how all these intricate parts work together as a single, cohesive system. You'll be equipped to follow and even contribute to those technical car discussions with confidence. Let's start with the engine. Its fundamental job is to turn fuel into motion. But how it does, that varies dramatically. The physical layout, or architecture, is a key factor. You have inline engines, where cylinders are in a straight line, V engines, which arrange them in a V shape for compactness, and boxer engines, where pistons move horizontally in opposition. Inside, a crankshaft converts the up and down motion of the pistons into rotation. The camshafts, driven by a timing belt or chain, open and close valves to let air and fuel in and exhaust out. But modern engines are much smarter. Technologies like VVTi, VTEC, or VANOS dynamically change when and how much these valves open. This allows an engine to be efficient at low speeds and powerful at high speeds. Fuel delivery has also evolved. Port injection sprays fuel just before the cylinder, while direct injection sprays it right inside, offering more precision and power. Then there's how the engine breathes. A naturally aspirated engine relies on atmospheric pressure to draw in air, but to force more air in and create more power, engineers use which are powered by exhaust gases, or superchargers, driven directly by the engine. Of course, all this power generates heat and friction. A cooling system circulates coolant to prevent overheating, while a lubrication system pumps oil to keep moving parts from seizing. Finally, to keep our air clean, emission systems like the catalytic converter, exhaust gas recirculation, and particulate filters neutralize harmful pollutants before they leave the tailpipe. Once the engine creates power, the transmission's job is to manage and deliver it to the wheels. You might be familiar with a manual transmission, where the driver uses a clutch pedal to disconnect the engine and select gears. A traditional automatic uses a hydraulic system and a device called a torque converter to shift gears for you. Then we have the dual clutch transmission, or DCT, which is like two manual gearboxes working in tandem. One clutch handles the odd-numbered gears, and the other handles the even ones, allowing for incredibly fast, seamless shifts. Another type is the continuously variable transmission, or CVT. Instead of fixed gears, it uses a belt and pulley system to provide an infinite range of gear ratios, keeping the engine at its most efficient speed. The power then flows to the final drive and the differential. The differential is crucial. It allows the outside wheel to spin faster than the inside wheel during a turn. An open differential is standard, but performance cars often use a limited slip differential, or LSD, to send more power to the wheel with more grip, preventing wheel spin. Finally, the drivetrain layout determines which wheels receive power. Front-wheel drive pulls the car, rear-wheel drive pushes it, and all-wheel drive, or four-wheel drive, powers all four wheels for maximum traction. Each setup offers a different balance of performance, efficiency, and handling. The modern car is as much a computer as it is a machine. A network of electronic control units, or ECSCs, acts as the car's brain. These modules receive information from hundreds of sensors, monitoring everything from oxygen levels in the exhaust to wheel speed, steering, angle, and pedal position. Systems like drive-by-wire mean your accelerator pedal isn't physically connected to the engine. It's an electronic signal telling the ECU how much power you want. This digital control enables sophisticated safety systems. Anti-lock brakes, or ABS, use wheel speed sensors to prevent your wheels from locking up during hard braking, allowing you to maintain steering control. Traction control does the opposite. It prevents wheels from spinning during acceleration. Stability control takes it a step further, using multiple sensors to detect a slide and can apply individual brakes to help you regain control. All these systems are driven by software, which is why a simple software update can sometimes change how a car drives. When a sensor fails, it sends bad data to the ECU, which can lead to warning lights, poor performance, or reduced fuel economy. Now, let's talk about what connects the car to the road: the suspension and steering. This isn't just about a smooth ride, it's about control. The suspension's geometry, the precise angles of its components is critical. Parts like control arms and bushings locate the wheels and allow them to move up and down. Sway bars connect the left and right wheels to reduce body roll during cornering. The core components are the springs, which absorb bumps, and the dampers, or shock absorbers, which control the spring's movement to stop the car from bouncing. Coilovers simply combine these two into a single unit. High-end cars may feature adaptive or air suspension, which can change stiffness or ride height on the fly for comfort or sport. Steering systems have also advanced. Old-school hydraulic power steering uses a fluid pump to assist you. Modern electric power steering uses an electric motor, which is more efficient and allows for features like lane-keeping assists. Finally, wheel alignment. The angles of the wheels relative to the car is defined by camber, caster, and toe. Proper alignment is vital for tire wear, stability, and handling. Braking is about more than just stopping. It's about controlled deceleration. Most modern cars use disc brakes, where a caliper squeezes pads against a spinning disc. Some vehicles still use drum brakes on the rear wheels, which are less powerful but cheaper. Brake bias refers to the distribution of braking force between the front and rear wheels. More force is sent to the front because weight shifts forward when you slow down. We mentioned DABs, but there's also brake assist, which detects a panic stop and applies maximum braking force for you. Hybrids and electric vehicles introduce regenerative braking. When you lift off the accelerator or press the brake pedal, the electric motor acts as a generator, converting the car's kinetic energy back into electricity to recharge the battery. This not only improves efficiency, but also reduces wear on the traditional brakes. These braking systems are fully integrated with stability control, working together to keep the car safe and stable under all conditions. The automotive world is constantly evolving, with new technologies emerging all the time. Hybrid systems combine a gasoline engine with an electric motor to improve efficiency. Some can run on electricity alone for short distances. Full electric vehicles eliminate the internal combustion engine entirely, relying solely on batteries and electric motors. To save fuel, many modern gasoline cars use start-stop systems that automatically shut off the engine when you re-stopped in traffic. Cylinder deactivation does something similar while you're driving, shutting down some of the engine's cylinders under light load to conserve fuel. Performance cars might use active aerodynamics, with wings and flaps that adjust automatically to increase downforce in corners or reduce drag on street. And of course, there are advanced driver assistance systems, or ADAS. These include everything from adaptive cruise control that maintains a set distance from the car ahead to automatic emergency braking and lane-keeping assist, all paving the way for a more autonomous future. It's crucial to understand that a car isn't just a collection of parts. It's a system of systems. Of course, we haven't talked about the most obvious parts, like the wheels, tires, steering wheel, or pedals. These are the primary interfaces between you, the car, and the road. They are undeniably important, but they are also the components most people already understand. The goal of this video was to look beyond those basics and illuminate the complex engineering that makes a modern vehicle function. So, the next time you hear someone mention a dual-clutch transmission, direct injection, or an adaptive suspension, you'll no longer feel lost. You now have a foundational understanding of what these systems do and, more importantly, why they matter. You can appreciate the incredible interplay of mechanics, electronics, and software that gets you from one place to another. Cars are complex, but they are not incomprehensible. Hopefully, this has demystified the machine for you. Thank you for watching. If you found this helpful, consider subscribing for more deep dives into the world of automotive technology.